So, in the previous lecture we talked about various kinds of logic gates. These are digital circuits which take digital inputs and give you a digital output, and basic gates are NOT and OR, which I discussed how to realize them using transistors basically. And then two more gates I talked about. One was this NAND gate and other was NOR gate. So, AND is you know what is AND, the NAND is not of that. So, that is NAND, and the symbol is also of that variety. This is the symbol for AND and this circle makes it NAND, and similarly if you have OR, then not of that is NOR. And these two are called universal gates because any kind of digital circuit can be made only through NAND gates or only through NOR gates. So, if you have a packet with lot many NAND gates, then you have enough material to make any circuit, digital circuit. So, today I will be trying to tell you the circuit which can be used for adding binary numbers. Okay. So, let me first draw the truth table and then see what kind of circuit will give those outputs. So, when you add two binary digits, you have two output results, and this is let us say A, this is B. So, it can be 0 0 or it can be 0 1 or it can be 1 0 or it can be 1 1, and then you have sum and then you have carry. Okay. So, 0 plus 0 will be 0, sum will be 0, carry will be 0. 0 plus 1, the sum will be 1, but no carry. 1 plus 0 is also the sum is 1 and no carry, and here 1 plus 1 is sum is 0 and carry is 1, because when you add 1 and 1 you get the next number which is 1 0. So, the sum is this and this is the carry, and otherwise the carry is 0 and this is 1. So, here this is the truth table. Now, how to implement that? How to get a circuit, digital circuit which can do this? If you look at this part only, one output. So, two inputs and one output, and the truth table is 0 0 gives you 0, 0 1 gives you 1, 1 0 gives you 1. Up to here it looks like OR gate, right. In OR gate the truth table was A, B and then Y. So, OR we said that 0 0 is 0, 0 1 is 1, then 1 0 is 1 and 1 1 is also 1. That is our OR gate. At least one of them is 1, then this is 1. Both of them are 1, then also it is 1. So, up to here if you compare, 0 0 is 0, so 0 0 is 0, 0 1 is 1, 0 1 is 1, 1 0 is 1, so 1 0 is 1. But then the last line here 1 1 is 1, here 1 1 is 0, that is a difference. So, if both of them are 1, then it becomes 0. If both of them are 0, then anyway it is 0. If 1 is 0, 1 is 1, then you have the output as 1. Now, this also has a special name. This also has a special name. If you make this thing 0 here, this thing 0 here, this is known as exclusive OR, and it is written as XOR. This is called exclusive OR or XOR. So, this is also kind of a gate, and it is important. So here if I see, the sum is nothing but XOR of A and B. How to implement that? Let me tell you the circuit and then we will check it. So first make 4 NAND gate. We will construct this digital circuit to give me this kind of output with 2 inputs and this kind of output. I will give you the circuit made from NAND gates only. So first draw 4 NAND gates. So these are 4 NAND gates, and here are the 2 inputs A and B. Okay, then output of this first NAND gate, that goes as an input here, and that also goes as input here, one of the 2 inputs. And then the second input comes from this A point itself. So this goes here, and then from B this goes here. So these are the 2 inputs for this NAND gate, these are the 2 inputs for this NAND gate, and then these 2 outputs, they go here, and this is your final output Y. This is how 4 NAND gates are added or connected in a circuit, so that you have this kind of exclusive or coming out. So let's check. 0 0 should give me 0. Let's start with 0 0. If A is 0 and B is 0, what happens? First come this side. 0 and 0 is 0. So here it is 0. And then naught of this is 1. And therefore this is 1 and this is 1. So 1 here and 1 here. Right? 0 and 0, and of 0 0 will be 0, and NAND of 0 0 will be 1. So this will be the output 1, and that 1 is going here, that 1 is going here. This is 0, so the other input here is 0, and this is 0, so this other input here is 0. Now 0 and 1, A and D and 0 and 1 is 0. Ready reference, if you want I can write, and the truth table is A, B, Y. 0 0 gives me 0, 0 1 gives me 0, 1 0 gives me 0, 1 1 gives me 1. This is AND. Only if both of them, A and B, both of them are high, then only the output is high. So 0 and 1, 0 and 1 is 0, so it is 0 here, and then naught of that is 1, so here are getting 1 here. Similarly 1 and 0, that is 0, and then naught of that, that means it will be 1 here, so you get 1 here. What is AND of 1 1? That is 1. A 1 1, the AND is 1. So you are getting 1 here, and naught of that is 0 here, so you are getting 0 here. So 0 and 0 gives me 0, so this first line is done. Then consider what happens if A is 0 and B is 1. So A is 0, B is 1. So let me remove this, let me remove this, and of course A is 0 is all right, and then the output can change. So all these things let me remove. So now you have 0 and 1. So this is 1. And this 1 goes here. So this will be 1. 0 and 1 is 0. So here it is 0, here it is 1. And therefore this is 1 and this is 1. And then 0 and 1 is 0. So here it is 0, here it is 1. So this is 1. And 1 and 1. How much is 1 and 1? Is 1. And naught of that will be 0. So this is 0. 0 and 1 is 0 and not of that is 1. So, this y will be 1. Okay, let me repeat. I have given a equal to 0, b equal to 1. So, 0 and 1 is 0. So, here it is 0, here it is 1. That one goes here and that one goes here. Then this 0 I am putting here directly, this one I am putting directly here. Now, 0 and 1 is 0. So, here it is 0, here it is 1. So, this is 1. And then this side 1, 1 is 1 and then not of that is 0. So, it is 0. 1 and 0 is 0 and therefore, not of this is 1. So, it is 1. So, 0 and 1 is giving me 1. So, this line is okay. And you understand, if this line is okay, then this line is also okay. Last one, 1 and 1. A is 1 and B is 1. So, both A and B are 1. This is also 1. So, this 1 reaches here. And what happens this side? 1 and 1 will be 1. And not of that will be 0. So, this is 0. So, this is 0 going here and this is going 0 here. Correct? 1 and 1 gives you 1. Not of that is 0. That 0 goes here, that 0 goes there. And this 1 is directly fed here. This 1 is directly fed here. So, what is 1 and 0? Let me remove all these old writings. So, what is 1 and 0? 1 and 0 is 0. So, this is 0, this is 1. So, this is 1 here. And similarly, 0 and 1. So, and is 0 and not is, so this is 1. Now, 1 and 1 is 1 and not of that is 0. So, this y becomes 0. So, that is the last line. Okay. So, this is the circuit realized with NAND gates and this is XOR. And this is also the sum. If I take this arithmetic addition, if I take this arithmetic addition, it is this S, 0, 0 gives 0, 0, 1 gives 1, 1, 0 gives 1 and 1, 1 gives 0. So, this is essentially, this y is nothing but S. S. Okay. So, this is our circuit for getting sum. Now, look at this table and for carry, A and B are input and this carry C is the output. So, if you look at it carefully, 0, 0 output should be 0, 0, 1 output should be 0, 1, 0 output should be 0, 1, 1 output should be 1. It is nothing but AND gate. The C is just AND of A and B, and therefore, from this A and B you have to just feed this A and B into an AND gate and that is it. Okay. And how do we create AND gate from the NAND gate? So, do you remember how you construct AND gate from the NAND gates? Right? You take two NAND gates, your input go here A and B, these are the input points, and then this output is fed to both the terminals and this is Y. So, you can very quickly check that this is AND gate 0 0. So, if this is 0, this is 0, here it will be 0, here it will be 1. this will be 1, this will be 1. So 1 and 1 is 1, and the not of that will be 0, so it is 0. And similarly you can check all other 1, 1 should be 1. So if these both are 1, then 1 and 1 will be 1 here, not of that will be 0 here. So 0 goes here, 0 goes here, 0 and 0 will be 0, and not of that will be 1, so that is 1. So you can check that this is it. So for carry, I only have to do this AND operation between A and B, and for that I have to take this A and B through one NAND gate. Output I have to feed in second NAND gate, both the inputs, and then I get. So already I have here this A and B are going through this NAND gate. So this point I already have it here. Correct. A and B are going into a NAND gate and output of that. A and B are going into the NAND gate and output of that. That I have to feed in another NAND gate at the two input points. So I take another NAND here, and then from this point I give both the inputs, and this will be our carry. Right, this NAND and this NAND will make AND, and A and B is nothing but the carry. So this circuit will give me both S and C. From here I can get S, from here I can get C. Now this circuit is known as half adder circuit. Half adder circuit. Why it is half adder circuit? Because when you actually add two numbers and the carry goes to the digit on left, you have three numbers to add and then get another sum and another carry, right. So if you have in decimal also, if you have something like this, then you put 7 plus 6 is 13, so this is the sum and this is the carry. Now you have to add all these three. So the full adder means there are three inputs A, B and C, and they are some operations are done, and then a sum is created and a carry is created. So this is known as half adder circuit, and if I do a sum of 3 digits and then find what is the sum, what is the carry, then it is called full adder circuit. So I will give you a broad idea of how this full adder circuit can be designed, and there will be 3 inputs that you understand. 2 numbers are to be added, and then the carry, all 3 are to be added. So let me first do this arithmetic with some number. So let us say we have some number here, and we have to add. So this is let us call it A, let us call it B. So what we do, and this is our carry. So initial carry is always 0. Once you are in the rightmost position, initial carry is always 0. So what we do is we first half add these two A and B, half adder operation. So if you do this half adder operation, so let me write it here. Let me do it let me write it half adder here. So let us say this is a half adder circuit, and then I have 2 input points, and these 2 input points I put A and B here. This A and this B I put here. What do I get? When I do this, I get sum as this is my first half adder, remember, and I get a sum which will be 0. I will get a carry which will be 1. But this is intermediate, this is not the final carry and final sum, because I have not taken care of this carry here. In this particular situation it is 0, it will not affect, but later on it will affect. So this is only an intermediate sum and intermediate carry. So let me write it SI and CI. Now this intermediate sum and this carry here, they are to be again they should go through this half adder thing, and then you will get the final sum. right? So if I put another half adder here, let's see, let me put another half adder here. And I say that the sum that I am getting from this, so this is the sum point, this is the carry point, you know, in the half adder you have two output. So this sum and that carry, and here that is the carry. So this carry and this sum, they go here, and then the sum, this is our final sum. This is our final sum. Check. This is the output of this first half adder, which is 0, and then the carry is 0, 0 and 0. If you do this half adder thing, that will give you sum as 0. So this is the sum. And how do you get the carry, final carry? Let me tell you how to get that final carry. You have a carry here and you have a carry here. These two, look at these two and the final carry, and construct the truth table and see what kind of circuit is needed here. So these two carries will finally, these two intermediate carries will finally make this final carry. So let me take a number. So say, let's say C1, 0, 0, 1, 0, 1 here, 1 here, 1 here, 1 here, 0 here, 0 here, 1 here, 1 here, any number you take. Now I am focusing on this carry, and this carry, the two intermediate carries and the final carry. So let me call this as a C1. Let me call this as C1, and let me call this as C2, and that is C. So let me make a table here, C1 and C2 and C. What is C1? When you add this A and B, this is A and B, this is our C. So when you add this A and B, what carry you get? That is our C1. So 1 and 1 if I add, what do I get? I get a sum of 0 and a carry of 1. So my C1 is 1. Here my C1 is 1. And what is C2? C2 is this. When I am adding this carry and this sum, what is the sum here? The sum is 0. When I am adding this and this, I am getting a sum 0. And this sum 0 is to be half added to this carry, which is 0. So the 0 and 0. 0, 0 are going here, and therefore the carry will be 0. So C2 is 0. So C2 is 0. Alright, and this position is C. So what is C here? This will give you 0 here, and this will give you 1 here. So C is 1. Next come this column. A, B, AB. AB, when you half add, once again you get sum as 0 and carry as 1. So C1 is once again 1. C1 is 1. And what is C2? C2 is, what is the sum here? The sum here is 0. And what is this initial carry? That initial carry is 1. Okay, so 1 and this 0, that is going into this half adder. What is the carry? If 1 goes here, 0 goes here, the carry is 0. So C2 is 0. And then you know the one, it will be 1 here and it will be 1 here. So your C is once again 1. Now see here, look at this. 0 and 0. This is A, this is B. 0 and 0. The sum is 0 and the carry is also 0. 0, 0. A and B going here. The sum is 0, the carry is 0. And this carry, so C1. So this is C1. So C1 is 0. This C1 is 0. And then come here. The sum is 0. And the original carry. Okay, the sum is 0 and the original carry 0 and 1. So what will be the carry? 0 and 1, the carry will be 0. So, this will be 0. Okay, and what is the carry here? Final carry? This will give you 1 and 0 carry. So, it is 0. Alright, so I think I have covered all the cases. 1 0 gives me 1, and naturally 0 1 will also give me 1. 1 0 is giving 1, 0 0 will give you 0. What about 1 1? C1 is 1 and C2 is 1. Now, see if you can construct an example in which this C1 is also 1 and C2 is also 1. And if you can construct such an example, then look what is that final C coming out, and then fill this row. But this will be a very interesting and funny task. Try that. But these things, if you look at it, these things, this can be implemented using an OR circuit. If you do C1 or C2, then you will get this C. 1 0 gives you 1, 0 0 gives you 0, and if you have 1 1, that will also give you 1. Okay? So, here I have to put in OR circuit, and that output will be the final C. So, you have final S, you have final C. Now, this is the mechanism, this is the procedure to design a circuit, say using NAND gates. I have already told you how to do that for half adder. I have already told you how to do for half adder, and I have already told you how to design an OR circuit using the NAND circuits. So, if you put all those so many NANDs here, you can just get that particular circuit. Okay, try it out, you will enjoy. So, with this I will close this course on physics of semiconductors. It was a long course, 36 lectures, 12 weeks, but I hope you have enjoyed the course and you have also enjoyed the quizzes, I believe, and we will look for many more interactions in future courses. Thank you.